All right, I welcome you all to another session of live interaction in principles of downstream techniques in bioprocess. So, this will be our fifth week. Do let me know if my screen is visible. It is, right? And feel free to unmute yourself and speak, and also use the chat box. Urja? Urja Narang has raised her hand. Is it by mistake, or do you want to speak something, Urja? Okay, let's start today's session. We'll be looking into practice questions under the topic adsorption, and we have just 8 questions for today. Thank you, Urja. So let's get into the questions. As usual, I expect you all to respond to these questions. Take a minute, and I hope you went through the lectures because otherwise, I don't think you can calculate an answer. Right? First question: pressure drop in a packed bed is 2.45 bar. If the velocity is increased, that's wrong here, is increased by 50%, what will be the pressure drop? So the velocity is increased. Remember that pressure drop was said to be proportional to length, velocity, inversely proportional to diameter. And maybe I should write it as does anybody want to take a guess? So here we are assuming no other parameters change. If only the velocity is increased by 50%, how will the pressure drop vary? Okay, let me help you all. So if I took delta P as some constant K into L V square by D, and since no other parameters are changing here, let me group KL by D together and V square separately. So all these are constants, so I'm not going to worry about them. Close. Let me rewrite delta P is equal to KL by D into V square. So all these are constants, so I'm not going to worry. So delta P2 by delta P1 is equal to V2 by V1 the whole square. Is that agreed? Taking this further, delta P2 by delta P1 is equal to, what is velocity 2? It is 1.5 times of velocity 1. Correct? If something is increased by 50%, what does that mean? It is 1.5 times of V1. Only then you find a a half part increase, or by zero point 0.5 it has increased over and above V1, correct? So if I cancel these two, what do I have? 1.5 square. What is 1.5 square? 225, right? 2.25. So delta P2, or the pressure drop in case 2, is 2.25 times of delta P1, which is 2.25 into 2.45. What's the answer? 5.5125 bar. So I'm going to approximate it as 5.5 bar. Okay, clear? Alright, let's go. So we got 5.51 bar as our answer. Moving on to question 2. Pressure drop in a packed bed is 4.5 bar. If the bed length is tripled, what will be the new pressure drop? So we just solved a very similar problem. So I'm going to wait, and you guys are going to tell me what the answer is in the chat box. Okay, let's take a minute or two. For people who are just joining, this is our second problem, and we did a very similar problem just a minute ago. For the new joinees, I'm going to write it again. Pressure drop is proportional to length square of velocity and inversely proportional to the diameter. And here the bed length is varying, and we are assuming all other parameters remain the same. So what is the new pressure drop? Okay, I'm going to go ahead and answer this too. But you should. This is our fifth class, guys. You don't have to be shy anymore. Delta P, if I had a constant that had all the terms to account for the proportional nature, and if I had KL V square by D, I'm going to group K V square by D now is constant and keep L outside, right? So these are constant. So on dividing them, I can cancel them out, right? So delta P2 by delta P1 is equal to L2 by L1. Is that okay? Which means delta P2 is equal to L2 by L1. Thank you, Jyoti and Sriram. Jyoti, check your answer again. Sriram, you're right. Into delta P1. So what is length 2? It is tripled, correct? So it is 3 times L1 divided by L1 into what is the first pressure? 4.5. That looks like 3. So 4.5 bar, right? So I can cancel the L's. And what is 3 times 4.5? 2 times 4.5 is 9 plus yeah, plus 4.5 is 13.5. Correct. Agreed. Let's check the answer. Yes, we fall in the range when there's no need for any range here. Good, Jyoti. So it is 13.5 bar. Third question, this is a very straightforward question. I've tried to confuse you a little here. Let's see if you get it right. You can just type in the option A, B, C, or D. Okay, fixed first law of diffusion states flux is equal to A, diffusion coefficient into dc square by dx square, B, diffusivity into dc square by dx square, C, diffusivity into dc by dx, and D, dc square by dx square. You have a very similar question, in fact the exact question in your assignment. So if you are clear with this, you will be clear when you answer that. What is it? Option A, B, C, or D? Good, Urja. Anybody else? You shouldn't be taking so much time. First of all, if you are confused if diffusion coefficient and diffusivity, there's diffusivity here and there's no term here. It's directly dc square by dx square. First of all, Fick's law gives the proportionality. How do you say? I mean, it states where diffusion would occur, and it is in the direction of negative concentration gradient, right? So higher to lower concentration is where diffusion occurs. So the gradient is given by dc by dx. So with distance, how the concentration varies, and there is no square term. So that removes three options. But this might confuse you. Diffusion coefficient and diffusivity are the same. They can be used interchangeably. Okay, the dA term that you have, DAB or dA, whatever you have, this capital D in the front is the proportionality constant, which denotes the diffusion coefficient or diffusivity or the ease of diffusion. Okay, so option C is the right answer. So in future, if people use this interchangeably, you shouldn't think it's something else. Okay. Question 4. If the breakthrough time is 6 hours and the difference between breakthrough and exhaustion times is 1.25 hours, what is the fraction of bed loaded? Again, take 2 minutes. We have all the time in the world. It's just 8 questions. At least we have all the time till 7:15 or 7. I will draw the profile here to just remind you. Here X is the solute. So solute concentration rises after a point. Maybe you can call this exhausted right here. And by the way, I'm just waiting for you to give me the answer. Don't sit watching me draw. Any answers? Since I have the x-axis cluttered, I'm writing the times there. If the breakthrough time is 6 hours and the difference between breakthrough and exhaustion time is 1.25 hours, which means T is at 7.25 hours, what is the fraction of bed loaded? Right? What is the formula for this? See, it won't help if you directly come to my live session without going through the lectures, right? You won't be able to immediately follow the question and give the answers. So fraction loaded is equal to 1 minus delta T divided by 2 TB. What is delta T? T minus TB, correct? And they've directly given you what T minus TB is, 1.25. In this you know as 6. So when you substitute 1 minus 1.25 divided by 2 into 6 is equal to 1 minus 1.25 by 12. What is that? 1.25 divided by 12 is 0.10, 0.10416. So I'm going to round that off as 1042. That gives me an answer of 0.8958, which I'm rounding off as 6. Okay, so what is the fraction of bed that is loaded? 0.896. What percentage is it loaded? 89.6. But since they have just asked you the fraction, you can go with this 0.896. Is it clear for everybody? Sriram, that's a great approximation, 0.9, but I'm having it at 2 decimals because I think in your assignments they generally expect at least 2 decimals. Again, if you were to round this off 6 as the next decimal, yes, Sriram, you're right. Yeah, 0.89 to zero point 0.9. Zero point 0.9 is a good approximation. If I had, you know, kept this at zero point 0.1, then 0.9 is the right answer, or even 0.104. Okay, agreeable? Can we move on to the next question? Which of the following is desired? Short breakthrough time, small difference between breakthrough and exhaustion times, large difference between breakthrough and exhaustion times, and low fraction of bed loaded. I think you had one more similar question in your non-graded assignment, which was also interesting. It had which one of the following is not desired, correct? So if you answer these two questions, you'll be very clear about what you need in a packed bed adsorber. again I'm going to draw a profile. Which of the following is desired? So this is the equilibration zone, is it? I hope I'm right. Correct me if I'm wrong. Okay. This is the equilibration zone, and this is the adsorption zone, right? Breakthrough is when the beads or the adsorbent material has adsorbed to its maximal capacity, and beyond this time the solute starts coming out or showing up in the outflow, right? The stream that comes out. So is it desirable? Short breakthrough time is, so the longer it takes for a bed to saturate, the better it is. Correct? Breakthrough time is when the adsorbent material is beginning to saturate. So beyond exhaustion, it's not going to adsorb anymore. So the more you delay breakthrough time, the better is the efficiency of the process. So shorter breakthrough time or short breakthrough time is undesirable. Next, small difference between breakthrough and exhaustion time. Large difference between breakthrough and exhaustion times. Option D, low fraction of bed loaded. We just did a problem where we saw that the fraction of bed loaded is about zero point 0.9, which means 90% of the adsorbent material was loaded before breakthrough, or including breakthrough or before exhaustion, let's say. Correct? Which is good. However, if you have a low fraction of bed loaded, let's say you have zero point 0.4 or zero point 0.3, what does that mean? Only 30 or 40% of the fraction bed is loaded, and already you have reached exhaustion. That's not good, right? Which means you do not have the right adsorbent material for your solute or your adsorbate. Yes or no? So the fraction has to be as high as possible. So again, this is wrong. And then you have two options in the middle: small difference between breakthrough and exhaustion times, and large difference between breakthrough and exhaustion time. So let's consider this as small. You have one more area where, let's say, the difference is large. Let me make it even more larger. And then I have one more case where the difference between breakthrough and exhaustion is smaller. Don't mind the dancing lines, but you get the point, right? So let's assume the breakthrough is around the same time for both. You have exhaustion very early in case of the green line, and then you have exhaustion coming later in case of the purple line. So what will you think? So you might think that if it gets exhausted late, it means it is working for a longer time. So I should go for something that gets exhausted at after 15 hours, whereas this green thing gets exhausted within 11 hours. So I should go for the purple colored line, or the first case bed. No, that's wrong, because you should compare the breakthrough. And the breakthrough is same for both cases. If between breakthrough and exhaustion the time is very less, it means, say, let's say at 10th hour it breaks through. In 11th hour you are able to exhaust the bed. By after 11 hours you can immediately move it to the next bed, or you can start regenerating or do something. Whereas in this case, again at 10th hour there is breakthrough, but you have to wait 4 long hours for this to saturate or completely exhaust itself before you can regenerate or transfer the feed into another tubular bed or packed bed. Correct? So the time between breakthrough and exhaustion has to be as low as possible, so that the whole process is more profitable for you. And also it has to be immediate. It also shows how efficiently your adsorbent material absorbs. So immediately everything is, if all the sites are full, it should, the solute should, the adsorbate concentration in your stream should immediately peak and attain that saturated plateau region here. Correct? If it happens very slowly, it means that the rate of absorption itself in your bed or the absorbent is very low or inefficient, not the best. Correct? So large difference between breakthrough and exhaustion times is undesirable. Let me cross here. So that leaves only option B as your right answer. Did everybody understand this concept? Can I proceed? So if you understand this, you can answer the other question on your non-graded assignment. What is not desired? Okay. Option B is your right answer. Let's go into question 6. A stream at a flow rate of 2 liters per minute containing 0.25 gram per cc of impurity is entering an adsorber. 20 cc of fresh activated carbon is added to remove the impurity. What is the percentage removal if the adsorption follows a linear relationship with constant 12? Take 2 minutes. First, write down what are all the given. The flow rate F is equal to 2 liters per minute, which is 2000 ml per minute, containing, so you might have seen the lectures having XF, but I'm very used to using X naught because this F confuses me with the feed here. So I'm habituated to using X naught and X. So when I draw something, let's have a diagram here. So stream at a flow rate of 2000 ml per minute containing an impurity of 0.25 gram per cc. This is X, this is F, and I'm calling this X naught. Okay, is entering an adsorber. 20 cc of W is equal to 20 cc. I'm going to call this again ml or cc if you want. It's up to you how you all this gram per cc, gram per cc. Okay, of fresh cubic centimeter, is it? Centimeter cube. It is right. Okay. Is added to remove the impurity. What is the percentage removal if adsorption follows a linear relationship with, and they've said fresh activated, right? Q. They're telling you that it is a linear 0.25 gram per cc. It's a linear adsorption isotherm. So Q is equal to K into X, where K is 12. So who can solve and give me the answer? The stream coming out will be F and X, Q and X. Again, instead of QF, I will be calling this Q naught, and this will be Q. Okay, how do you balance this? Input is equal to output, right? F into X naught plus W into Q naught is equal to F into X plus W into Q, correct? So F into X naught minus X is equal to W into Q minus Q naught, correct? And here, since it's fresh, Q naught is 0. So what is F here? 2000 into X naught is 0.25 gram per cc, and this is going to be liters. I've converted into ml, so that's again cc per minute. We are going to ignore minute here because we are assuming the same time frame for both w as well as f. Okay, so cc and cc will cancel out. Okay, I'm just telling you here because I'm going to ignore the units and go forward. Is equal to w is 20. Put a slash here by mistake. It's 20 cc into what is q? 12 into x, correct? Which brings us to what is 2000 into 0.25? 2000 into 0.25 is 500. 500 minus 2000x is equal to 12 to the 24, 240 x. So if I bring this term here, x is equal to 500 divided by 2240, correct? If I bring this 2000x here, it will be 2240x and 500 on the other side. I just brought it here. We don't have much space left, so I'm skipping steps. 500 divided by 2240 is equal to 0.2232. Let's round it off at 0.223 for now. So if this is my x, so what have they asked you here? What is the percentage removal if the absorption follows a linear relationship? So how would you say percentage removal? X minus, sorry. So where did we start? X naught. Initial concentration minus final concentration divided by initial into 100 is equal to 0.25. Oops, sorry, I just pressed too hard. 0.25 into, I'm sorry, minus, where do we have this? 0.223 divided by 0.25 into 100. I hope it's legible for you all. Is it fitting within the screen? 0.25 minus 0.223 divided by 0.25 into 100. I'm getting 10.8 as my answer. What are you guys getting? Is it the same? Did you all work through these steps? Thank you, Shriram. So everybody's fine with this problem? Anybody wants a repetition? Okay. Yes, we got 10.8 as our answer. Yes, sure, Jyoti. So what did you see here? You're having a mass balance, correct? So start from here. This is your adsorber. You're having an inflow of some feed at 2 liters per minute or 2000 ml per minute, having an initial solute concentration or impurity concentration of 0.25 gram per cc, and then it is coming out with some other concentration which we don't know. And how is the concentration changing? Because the impurity from this feed stream is going into the adsorbent, which is provided by this stream. So a particular weight of adsorbent material is put inside this adsorber, and the X term impurity transfers from the feed stream into the adsorbent stream, the adsorbent material, and then it comes out with a different concentration. Now the adsorbent material has increased in the impurity concentration, and whatever impurity the feed stream had, it has lost a little. So I'm balancing these. On the left side, we have all the inputs. F into x naught plus W into Q naught is equal to F into x, the output streams, and W into Q. I'm calling Q naught and x naught for the initial ones, and x and Q for the final or the output flows. So I'm grouping the terms here. F into x naught minus x is equal to W into Q naught minus Q naught, because it's you have the output on this side, and logically also Q is going to be higher than Q naught, right? Whatever it came inside the adsorber is going to take away more impurities than it originally had. Otherwise, doing the whole process is stupid, correct? So it is going to have Q minus Q naught, and Q naught is 0 since it is a freshly activated carbon. So it does not have any initial impurities on its own. It's fresh. So this term is 0. So in the remaining terms, I'm substituting all the known values, and Q is linear, which means it is directly proportional to the constant which we know as 12. So I'm substituting that in place of Q. So we are solving for X. and we got the final x. This term here is 0.223. Okay, and then I'm subtracting this from 0.25 and dividing with 0.25 because you need to know what percentage of the initial thing we have recovered. And then I'm multiplying by 100 and I got this 10.8. Is that clear, Jyoti? Great. So I'm going to go to question 7. In problem 6, instead of fresh carbon, if we add used carbon containing zero point 0.5 gram per cc of impurity, what is the percentage removal? Again, it's the same problem, just a small change, and I want you all to sit and work on it. Now that I've repeated what I just did, it should have been, I hope, if not engraved, at least fresh in your memory so that you can attempt again, right? So I'm going to have x is equal to, I'm just writing here so that you don't have to, I mean, you can't scroll back. And what is x naught? 0.25, right? 0.25 gram per cc. Then you have W is equal to 20 cc and Q naught is K into X, and here instead of X we are going to have, let me directly put it in the bracket here as 0.5, and it's going to be F and X, it's going to be W and Q. Take a minute. Guys, I was just wondering, do you realize that the adsorbent actually has zero point 0.5 gram per cc, while this guy had just 0.25 gram per cc, right? Okay, let's wait for you all. I'll give you one more minute. I want you to work this out and tell me what answer you get. Okay. Shall we solve this? I've made a mistake here, so it's not K into Q naught. They have told you that it is zero point 0.5 gram per. Oops. What did I do? Oops. Yeah. 0.5 gram per cc. So this linear adsorption isotherm. So Q is equal to K into X, where K is 12. So that applies only within the adsorber or adsorber, right? So only during the process we are talking about an isotherm. So before in Q naught, it is not right to have K here, correct? The isotherm is for the process of adsorption. So this Q naught is, how do I say, this stream already has this particular concentration of impurity. So I should not be applying the constant there. So that's the mistake that I did. So I did a calculation while you guys hopefully were also working out. Does anybody have an answer or shall I start writing? So again, I'm not seeing any responses, so I'm going to start. We are going to do a mass balance. So F into X naught plus W into Q naught is equal to F into X plus W into Q. Again, F in, you can directly substitute in this stage also, X naught minus X, however comfortable you are, Q naught. And I know that, let me write it there only so that we save some space. W into, well, X minus Q naught. Now I'm going to substitute everything. 2000 into X naught is 0.25 minus X, I don't know, is equal to W is 20 into 12x minus Q naught is zero point 0.5. So I confused you a little with saying that Q naught is higher than X naught. Doesn't matter. The adsorbent can have a greater capacity to hold on to your solute molecules, right? Let's say this is the concentration of impurities in the adsorbent molecule, obviously we would expect the adsorbent to take in more concentration than the feed stream. So if the feed stream has some more concentration of this particular impurity, the adsorbent should still be able to accommodate more before it is completely exhausted and needs regeneration, right? So we need not worry about what this value is and how it compares with the x naught. So that was my because of this k issue I got a little confused. All right, so I hope we are all are clear now. I'm going to solve for this. 2000 into 0.25, I already know this as 500 minus 2000 x is equal to 12 2s are 240 x minus 12.20.5 is 10. Correct? So what would I have? 500 plus 10 is 510 is equal to again 2240 x. So x is equal to 510 by 2240, which is 510 divided by 2240 point 2276. Correct? I'm going to approximate this as 0.228. What did we get last time? We had 0.223, right? So there's a 0.005 gram per cc reduction more in case of fresh, and if you have used adsorbent, you're getting 0.228. Now again we are going to apply the formula for which color do you guys like, which is more easy to see visible, blue or red? So x naught minus x whole divided by x naught into 100 is equal to 0.25. Correct? 0.25 minus 0.228 divided by 0.25 into 100. So what is that? 0.25 minus 0.228 into 100 is 8.8. Does everybody get 8.8? So recovery, oops. Please excuse that. Recovery is 8.8%. Correct? So previously we had 10.8 with old, I mean freshly uh, introduced adsorbent, you had 10.8% recovery. But with used ones, used carbon, you're getting 8.8. That's decent, no? You're just having 2% decrease in recovery. Clear? Shriram is getting 9.2. How, Shriram? Maybe in the decimals, we might differ a little in the decimals. Where you take 8.1 to 9.2 is accepted, so Shriram is right. I think you take just one decimal, Shriram. Did you do 0.23 or something? And due to decimal, yes, Shriram. So I get 8.8, so I'm going to put it there, and then Shriram got 9.2. So let's put it there. Okay. Question 8. In a two-stage counter current adsorber, feed of zero point 0.1 liters per minute is entering the first adsorber. It contains zero point 0.1 gram per cc of impurity. Fresh carbon of 50 gram is added in the second stage, and it then enters the first stage while the liquid flows from the first stage to the second. Okay, it's already 7. We are going to take a little time in this. Does anybody want to try and tell me the answer, or shall I go ahead and solve this for us? Okay, until I draw the diagram, you can take to solve and give me the answer if you have it. We're going to have two stages of adsorption. Counter current adsorption feed of 1 liter per zero point 0.1 liter per minute. So I'm going to put that in ml, 100 ml per minute. If I make any mistake, please let me know. Feed is, and then it is entering the first absorber. It contains x naught is equal to zero point 0.1 gram per cc. Fresh carbon of 50 gram is added to the second stage. So W is equal to 50 gram going into the second stage, and it then enters the first stage, which means this output is the input for okay, I don't know how I'm going to draw that. Great. But you get the point, right? I should not try to make a straight line. Let me make a curved line and get done with it. Yes. So while the liquid flows from the first stage to the second, cool. So the flow, liquid flow, let me put that in blue so that we get an idea. So this liquid flow is going to continue from 1 to 2 and then outside. Correct? Only the adsorbent flow is in this fashion. Okay. So what does it say while the liquid blah blah blah? The adsorption follows a linear isotherm thankfully with K is equal to 12. So Q is equal to Kx where K is equal to 12. What is the overall fraction adsorption? I think they're asking the same fraction recovery like how we did for the previous two sums. Okay, this thing is going to be a little, I'm going to call this Q2. How shall we name this? Let's name this Q naught then. Since it's fresh, Q naught is going to be 0. Correct? And then we are getting Q2. And we are having Q1 is equal to. Now let's just have Q2 here because it's the same thing, right? So let's have it Q2 and let's call this as Q1. What do you say? Is everybody happy with the naming? We're having F here and we'll call this X1 and X. Let's try again X1 and this I'm going to call X2. Everywhere there's F. Okay, clear? Again everywhere you have W. It's the flow rate, so it's not going to change. Let's start with the mass balance now. For stage 1, I'm going to have F into X naught plus W into Q2. Correct? Is equal to F into X1 plus W into Q1. Agreed? F into X naught minus X1 is equal to W into Q1 minus Q2, which is K into, okay, let's get there later. So F is 100 ml and X naught is 0.1, correct? X1 we don't know, is equal to W is 50 grams and Q1 is uh, K into X1, correct? And Q2 is K into X2. So I can bring K out as 50 into 12 into X1 minus X2. Correct? So let me solve this and keep it as equation 1 here. 100 into 0.1 will be 10. Correct? Minus 100 x1 is equal to, what is 50 into 12? 12 is 60. 600 into x1 minus x2, which gives, if I get 600x and bring 100x, will be 700 here, right? 700 x1. Am I making mistakes? Please let me know. 700 x1 minus 600 x2 is equal to 10. This is my 1. Okay. Stage 2, I would love to get an extra page, but I can't see the question if I do that, right? I can try one thing. Keep limitations. Okay. Now, let's go for stage 2. What is this? So you're having f into x1 plus w, sorry, w into q, oops, w into q naught, correct, is equal to f into x2 plus w into q2, and q naught is 0, so this entire term goes to 0. So f into x1 minus x2 is equal to w into q2, which is again k into x2, correct? Let's substitute for all this. F is 100, x1 is 0.1 minus, that's not 0.1, x naught is 0.1, right? So that's x1 minus x2, both are variables, is equal to w into k. What is that? 600, right? Again, it's the same thing, 600 into x2, which is, let's multiply 100 x1. Okay. So if I bring it to this side, it's going to be 700, right? Huh. So 100 x1 is equal to 700 x2. That makes life very easy for us. X1 is equal to 7 times x2, correct? Am I making any mistake, guys? So if I use this in 1, what would I get? 700 into 7x2 minus 600 x2 is equal to 10. 7 sevens are 4900 x2 minus 600 x2 is equal to 10, which means 4900 minus 600, that's 4300, right? X2 is equal to 10, so 10 divided by 4300 is x is equal to 0.00232. I hope I haven't made any mistakes. 232, correct. This is x2 into 7 is your x1. X1 is equal to 0.016. I'm going to leave it at that, right? So overall fraction will be, I'm going to change color so that you don't confuse, x naught minus x2 divided by x naught into 100, which gives zero point 0.1 minus 0.9768 into 100 will be 97.68. Is this what you guys are all getting? I mean, by fraction it is 0.9768, by percentage it is 97, correct? So overall fraction absorption would be 0.9768. Let's just round it off by 97. Oops. Okay, where have we made mistakes? Did you guys feel something was off? Where did W go in stage 2? Okay, W has not gone. Q naught is 0, so this part vanished. We still have W here. So I put 50 here and K is 12 and I substituted. Are all the substitutions right? Urja, can you double check for me? Any mistakes? That's right, right? 700. We're at 0.97 and the answer should be between zero point 0.7 and zero point 0.8. Something's wrong. Okay. I mean, if you guys don't have any other suggestion where I might have gone wrong, maybe we'll close this and reopen this question in next class, maybe. Have I screwed up some decimal here? Any positive, negative sign problem? I can't find anything. Okay, in case you realize later, you can also post in the YouTube channel. I hope you guys look into it. I'll be uploading this video, so you can let me know in the comments where I've gone wrong, and we'll anyway look into it in the next class. Okay, thank you all for joining today's session. It was great having you back. Please do continue to attend these sessions. I hope it's useful for you. And with that, I think we can close this live session for week 5. Thank you all for joining. I'm going to stop